It's preparing.
We're live.
I see. All right. So let me welcome you all to this workshop on black holes, BPS, BMS, and integrability. We will have roughly 4 hours, 4 talks a day, 2 in the morning, 2 in the afternoon. The talks have the duration of 1 hour, followed by discussions. You're all welcome to ask questions during the talk. Please keep yourself muted, but then if you want to ask a question, unmute yourself. So the first speaker of today is Samir Murthy from King's College, and he will talk about the growth of the 1/16th BPS index in 4-dimensional n equals to 4 super young males theory. So Samir, thanks very much. Go ahead.
Okay, thank you very much for the invitation. It's a pleasure to pretend that one is in Lisbon and is having a nice coffee with friends. Hopefully that will be the case not too far in the future. My title is The Growth of the 1/16th BPS Index in 4-dimensional n equal to 4 super young males theory. Now this is based on some work I've been doing in the last couple of years, 2 or 3 years, in various combinations of collaborations with Alejandro Cabo Bisset, I think he's there in the audience, Davide Cassani, and Dario Martelli. I'll refer to the papers as we go along. So the main sort of central question that I want to address in today's talk has been around for about 15 years or so. And the context is really the original prototype example of the ADS-CFT correspondence. Actually, let me pause right away. Am I audible? Is it clear? Gabriel?
Good for me.
Yes. You're good.
Okay, actually, I had pinned Gabriel, but maybe I'll pin Suresh because.
Yeah, Samir, you're good. You're good to go.
Yeah, so it'll help. So the thing is, I can only see you. So it'll help if you sort of, if you don't restrain your natural expressions, and that's the only feedback I have. And also, if anybody has questions, please do interrupt and ask. It helps me a lot because I can't see you. Okay, so right. So take n equal to 4 super young males theory in 4 dimensions with a UN gauge group, and put it on an S3 times time. The dual of this, according to ADS-CFT, is a gravitational theory on ADS5 times S5, and the boundary of the ADS5 is the same S3 as the one that the field theory is living in. Here I've sort of tried to cut it in half to show the interior, and this theory admits a black hole solution, and one preserves 2 of the 32 supercharges of the theory. Okay, so these are 1/16 BPS black holes. And these are large black holes in the sense that the area of the event horizon in Planck units is parametrically large, and in particular, in the field theory units, it scales as n squared. Remember that G Newton in 5 dimensions is 1 over n squared. Okay, and the question is, can we understand this this entropy in a microscopic theory? Okay, so the natural place to look for is the dual theory, and to look at 1/16th BPS states in that theory. Okay, so there's this function called the superconformal index. I'll call it In of tau, n being the rank of the gauge group, which is essentially like a Witten index, trace -1 to the f, dressed up by various combinations of the charges coupling to some chemical potentials. And the question is whether the log of this index also has this n squared growth. Okay, and does it capture the black hole entropy, and in particular, does it have the n squared growth? And this question was first posed about 15 years ago and studied, and at that time, the answer seemed to be negative. And that sparked off a lot of research in this field to tackle this question. Okay, so recently this has been revisited, and that's what I want to discuss. First, let me say something about the question itself. This question is not only particular to n equal to 4 super young males. it's much more general. It applies to any n equal to 1 superconformed field theory in 4 dimensions, which has some kind of a large n dual. So imagine some gauge theory, for instance. Okay, and everything else in this slide is the same as the previous one, except that now the states, the theory has 8 supercharges, and the states therefore are 1/4 BPS. Okay. In fact, the black hole solutions that were written down here were originally written down in this context, in the theory of 8 supercharges in 5 dimensions. Okay, so as I said, there's been some recent progress, and the sort of conclusion seems to be that in fact the index does have an n square growth, and not just that, it actually captures the black hole entropy early on the nose, including all the numerical factors at large n. Right? So I want to that's what I want to tell you about. But in the first 15 minutes or so in the introduction, I want to first remind you of the problem, the details of the problem. It's been, not everybody's been thinking about it all the time, at least not these days. So I just want to tell you a little bit about what is this index, what are the black holes, and why there's supposed to be this relation between the two. Okay, and I'll also clarify what exactly does this mean. Okay, any questions so far before I start the details of the problem?
Samir, yeah, I have a question.
Yes, can you just identify yourself? Because the thing is, I have pinned Suresh, so I don't know who's talking.
So this is Abhiram. Hi, Samir. What is the Q over here that you're mentioning in the index? Are you going to clarify it? Or?
Yeah, I'm going to clarify this. So here, so QI were some generic charges. I'll not generic, but some specific charges, which I'll tell you about. And
Okay.
Q is also a specific charge, which I'll tell you about. That's one of the things I'm going to do in the introduction.
Okay.
Any other questions? Okay, so for now, if this is confusing, think about this as the most general index in which captures 1/4 BPS states. Okay, that's in fact, that was the slogan, one of the slogans of this paper, that the thing they write down is the most general index that captures 1/16 BPS states in n equal to 4 super n. So that's a good way to characterize. All right, so let me tell you what this index is to answer Abhiram's question. So n equal to 4, so these BPS states are labeled by their angular momenta on the 3 sphere and the R charges. And n equal to 4 super-Yang-Mills has an SU4 R symmetry group. So there are 3 Cartan generators. And in this more general context that I discussed, there's only one U1 R charge, and then there can be flavors. So indeed, this n equal to 4 super-Yang-Mills can be written in this language, and in which one of these 3 Qs become the R charge Q, and the other 2 become flavor symmetries. Okay, so this is the language I'm going to be using. And then in addition, there are 2 angular momenta on the S3. So these are the charges, the R charge Q, capital Q, J1, J2, and some flavors FA. And now there's a supersymmetry, which is curly Q, which has the following algebra. Q and Q bar, and the anticommutator of that equals this linear combination of charges. E here is the energy. Now, if you want to count BPS states using an index, then the thing to do so you want to ask what are all the states annihilated in the cohomology of this, and trace and count it with the minus on the BF. Then in the index function, what you can write is you can add charges, what I call small q there, which commute with the supercharge. Okay, so you have to ask what is the commutant, and any flavor symmetry by definition commutes with the supercharge. And of these 3 charges, J1, J2, and U1 R charge Q, there are 2 combinations, J1 plus half Q and J2 plus half Q, which commute with the supercharge. So the most general index is the following. You have trace minus 1 to the F times e to the minus beta QQ bar times a coupling to J1 plus half Q and to J2 plus half Q and to the flavors. Okay, so this is the most general index one can write down. Okay, now today I'm just going to talk about a simpler situation. Wait, before that. So firstly, we all know by standard arguments that this index is a function of beta, sigma, tau, and mu a, but in fact, it doesn't depend on beta. Okay, this is the standard argument that because of the minus 1 to the F, the pair and the pairing of the SUSY algebra, this cancels. Then to make life simpler, I'm going to actually turn off all the flavor chemical potentials. Everything that I say can then be dressed up to talk about the most sort of general complicated case as well. And we've also written a paper about that. Okay, but today, just to sort of make life simple and the presentation simple, I'll talk about the simple case. And in fact, I'm going to set sigma equals tau. So there's only one coupling to J1 plus J2 plus Q. Okay, and this combination, I'll call this small n in a second, that you should think of as labeling the BPS states. Okay, so this is the most general state. So this is what you have on the screen in front of you is the simplest, most general index. Okay, so you want an index which gets contributions from 1/4 or 1/16 BPS states. That's the case. Okay, so this is the thing I'm going to study. And now, if you write a Fourier expansion of this index, its coefficients are the ones which have the degeneracies here, dn of n. Okay. What did I want to say? Yes. So this index has a periodicity in tau, which depends on the quantization of J and Q. So J has some universal quantization based on the angular momentum on the sphere. The Q, which is an arc charge, is quantized according to the theory. Right. So here I've chosen to show n equal to 4 super Yang-Mills, where remember the arc charges have 1/3 or 2/3 plus an integer. Okay. So that's what I'm going to talk about. So there are two things. There's only one sort of label for the BPS state. I'm going to call that n, and dn of n is the degeneracy or the index degeneracy of that BPS of the ensemble of those BPS states. Yeah, there's another nomenclature, confusion in nomenclature. So this dn of n is a trace of -1 to the f in a given in the Hilbert space with a given fixed n, fixed charge n. So that's also called an index, and this in of tau is also called an index sometimes. Okay, so it's a bit confusing, and if I need to clarify it, I'll call this the degeneracy, the microcanonical object, the index, and this I'll call the index function. Okay, if I need to clarify. Okay, so both of them are functions of one variable. Very good. Any questions about the index? Okay, then I'll talk about the black hole. So start with type 2b theory on ADS 5 times S5. And again, we go to the more general context. You have minimal 5-dimensional supergravity in ADS 5. This has just the metric and the gauge field as the field content. And the 1/4 BPS black holes are labeled by 3 charges, J1, J2, and Q as before. And recalling that G Newton goes as 1 over n square, the charges here, it's useful to write the gravitational charges. So scale out n square and define small j1, j2, and q. And again, I'll talk about the simplest situation where j1 equals j2 equals j. Okay? In fact, this was the first solution that was discovered by Gutovsky and Real. And it's important that this is not zero. These black holes don't exist if they don't rotate. The solution becomes singular. And this was one of the reasons why this took such a long time to discover. This was only discovered in 2004. Okay, so now you have 2 charges, J and Q, but in fact, they're also not independent. They obey a nonlinear relation. You can write it out explicitly. Here I've shown you a graph, which at large charges goes as Q scales as J to the 2/3. Okay. This relates out of just looking at the supergravity solution. You write down the black hole solution, you calculate, measure all the charges, and you notice that there's a certain relation between. Okay. Now, so therefore, the black hole entropy can also be thought of after scaling out the n square as one function of one variable. Okay, so s, small s, some entropy density of j. This j is at large j is exactly n, small n, divided by n squared that I just defined. Okay, so you have one function in the gravitational theory and one function in the Yang-Mills theory, and the question is, are these two equal asymptotically? Okay, that's the main question. That's the expectation from ADS-CFT. What is this function? Let me just tell you what this function is. So here the x-axis is the charge n, and the y-axis is the entropy. And here is the function I showed you, and you can see the shape of the function. So it has some kind of j to the 2/3, excuse me, shape, which if you go along this line, and if you go along this direction, you'll see the growth in n square. Okay, this is just the first 10 values. Okay, and here for reference, I've shown you the entropy of a gas of gravitons with the same charges. Okay, it's very, very small. As n square goes to infinity, this thing goes to 0. All right. Now, it's useful to sharpen, because there's been so much confusion, it's useful to sharpen this statement mathematically. So firstly, this statement obviously is an asymptotic statement, but I'm abusing terminology. I should use an asymptotic sign, but like in all physics papers, I'll use an arrow sign. I also did that in my paper. So the question is there an asymptotic growth of states of the left-hand side, which is equal to the right-hand side? And what do I mean by asymptotics? There are actually two limits which people consider. One is the large N limit. So in this limit, the charge N and the rank N scales to infinity, such that the ratio N over N squared, the gravitational charge, remains constant. This is where the black hole solutions are written down. The other one is the Cardy-like limit. So this is because of, by analogy to two dimensions, that you fix the theory, you fix the central charge or the gauge group N, and then you just scale the charge to infinity. Right? Very large charges. That's the Cardy-like limit. And these two limits are independent. These two limits are independent. Okay? So there is a regime of overlap at very large charge and very large N. So you can, for instance, start here, okay, and fix this J, but then scale J to infinity, and you'll get the Cardy. Okay, but otherwise, neither of them is a subset of the other. All right. Now, any questions about this?
Yeah, Samir. Hi. This is Alejandra.
Hi,
if you can.
Mm-hmm.
So maybe you'll explain it a bit later, but from the point of view of how you define the D sub n,
yes,
the degeneracy,
mm-hmm.
Why are you getting, like, it was just basically Q plus J.
Yeah, Q plus 2.
Yeah, but exactly. So why are you getting like for instance, in the equation that you have written right now, you have like Q squared minus J, like.
Here, this equation is a gravitational equation. So this was in fact one of the puzzles. So this equation comes, as I said, so the gravitational solution is some highly nonlinear object, as you know very well.
Yeah.
And this comes out of measuring the area of the horizon.
Exactly, but from the field theory.
The puzzle is how does the field theory see this nonlinear?
Because yeah, my question is mostly motivated that from the field theory point of view, naively, well, since I guess this degeneracies haven't, been discussed too much in detail, I would have thought, oh, I could turn off J. But it seems
so like, J you can certainly not turn off, because as I said, when J
right,
from the field theory point of view.
Yeah, well, from the gravitational point of view, of course, yeah, there's this regularity condition. Otherwise, they're like just this giant magnons types of like, or superstars.
Right.
I forget what the terminology was, but from the field theory point of view, it seemed quite like.
Right. So another way to ask it is, why is there this relation between Q and J?
Yeah, from the field theory point of view, like that's,
from the field theory point of view, exactly. So all this will essentially. I'll tell you everything that I know. This is part of the sort of unraveling of the puzzle. I mean, this was exactly why, this was one of the reasons, I mean, this was a technical reason why this problem was so complicated. Okay, this is unlike other, this is unlike the D1, D5 system or, Strominger alpha black hole. Okay, so this is one of the reasons why I think people were stuck. Okay, I hope I can answer this question by the end of the talk, but please to ask me if this point is not clear by the end.
Okay. Thank you.
So I don't want to talk about this now because this is part of the story that I'm going to tell. Yeah?
Yeah.
Okay.
Thanks.
All right. So let's go on. Now I want to just flash, just as a definition. I mean, this is going to be the main player in the story, this index function. So I'm just going to flash a definition. It's an integral over UN matrices of an exponential of an infinite sum. This infinite sum, in each term, there's a trace u to the n, trace u dagger to the n, and its coefficient is governed by the so-called single letter index, which is again an explicit function. Here I've shown you the n equal to 4 answer, but this can be calculated for any n equal to 1 superconformal field theory. That's what was done in these original papers. And I don't want to review the derivation of this formula here because I think this is fairly well known. And also that's not very important what I'm going to say right now. So let me just tell you that you can, so in this paper, there's a Hamiltonian derivation and also here and maybe already here, but certainly in the last 10, 15 years, we understand it both from a Hamiltonian point of view as well as from a path integral point of view. In fact, in one of my papers recently, we clarified something there. Okay, so in the path integral point of view, the path integral localizes onto unitary matrices. Okay, that's one way to understand this. So for those of you who are aficionados of matrix models, one thing I want to point out right now, and this will play a role later, is that the potential of this model is purely double trace. So in terms of the eigenvalues, it's purely two particles. There's no one particle. Okay, this I'll expand on later. Okay, I just wanted to flash this and now tell you that yeah. So in the last, so since 2018 October, there's been a lot of progress, and by different methods, I think people have reached the conclusion that indeed there is a growth of states in the index, right? So and then there's been a mini explosion in activity in this field. Today I want to discuss three main questions. Okay, the first one is actually a gravitational question, but for me and my collaborators, this was, at least for me, well, also my collaborators, I think this was very useful to sort of sharpen and frame the puzzle. Okay, so I'm going to start there. And the question is, how do supersymmetric black holes contribute to the gravitational path entanglement? And if so, how do they do it? And the answer to this has to do with a very subtle BPS limit that one has to take in gravity and an associated regularization. Okay, I'll explain both the question and the answer as we go along. The second question, this is going to be the main point of the talk, is how can black holes be realized as large and saddle points of the matrix integral? And if they can be, are there other saddle points, and what do they mean? Okay, and this is the main story I'm going to focus on. And as I said, there are many different approaches to this. I myself have been involved in multiple approaches, but today I want to focus on this, which somehow I think is the cleanest from this larger point of view. And the answer relies on some very interesting relations to objects appearing in number theory, in particular this function called the Bloch-Wigner elliptic dialog algorithm. Okay, so I'll explain this. And finally, I want to discuss this puzzle which came after the original puzzle that was posed, namely that there's this lore that gauge invariant operators are gravitons, so how can they be black holes? Okay, so this has a very nice answer using the representation theory of UN, which this is a paper I wrote in May, and I'll discuss this at the end. All right. So let me pause for questions, because now I'm going to start with the three questions in turn. So let me pause for questions for a minute. Okay, very good. So then on to the first question. So let's go back to the basics. So why do we expect that the black hole entropy be log of this dn? Okay, so at the 0th level, I mean, this is like if you give a public talk, they will say, well, the black hole has a thermodynamic entropy according to Bekenstein-Hawking, and then the Boltzmann equation should say that that entropy should be a statistical entropy, and excuse me, there should be a large degeneracy of states. It should be the log of the degeneracy of states, and that degeneracy of states, according to SCFT, must be the degeneracy of states of the dual superangles theory. Okay, so this is sort of the basic idea. Now, as many of you know, there are many gaps in this argument. So firstly, at the philosophical level, this assumes a Hilbert space of quantum gravity, about which we know very little. Then the fact is that Boltzmann equation really talks about the degeneracy of states, and here dn is the index degeneracy. So the degeneracy of states is not preserved in the moduli space when you move from weak coupling to strong coupling. And thirdly, this index is only a lower bound on the total number of states. Okay, so there's no a priori sort of rigorous reason why these two should be equal without more information. Okay, these are all gaps, and these gaps sort of exist in all examples of black hole entropy, supersymmetric black hole entropy counting in string theory. And in other circumstances, in other contexts, these have been revisited in detail. So for instance, in flat space, black holes in flat space. And we've learned lots of lessons. And one of them is we should turn the problem around. We should start from the microscopic index. Okay. And there you calculate some Hamiltonian. So start from the microscopic theory, calculate a Hamiltonian index, okay, as trace minus 1 to the f, like I showed you. In the field theory, according to Feynman, this should be a functional integral. There's no issue about that. Okay, so write that as a functional integral. Then this index is protected, okay, and therefore it should be the same functional integral on the gravitational side, if you can make sense of it. But at least formally you can write that. Yeah, so as an aside, since the title of the workshop also says integrability, I should say that I'm not, I had some confusions about, I mean, people had confusions about this. I'm not discussing the dimension of 116 BPS operators, which are famously not protected. Okay, I'm just talking about the total number of states, bosons minus fermions. Okay, so you have a functional integral in ADS gravity. And then the question is, so this functional integral, for the index means that you use some supersymmetric boundary conditions in ADS gravity. And the question is, does the supersymmetric black hole contribute to this functional integral? Okay, and this is a subtle question because supersymmetric black holes, so firstly, when I say when I say functional integral, I always mean Euclidean theories. And in the Euclidean theory, the supersymmetric black hole has some kind of an infinite tube. Okay, so infinite means, so there are two infinities. One infinity comes from the UV of the ADS. That is a standard infinity which comes with ADS CFT. Okay, this was clarified in the very early days of ADS CFT, led to holographic renormalization. I won't discuss that. I'm talking about the IR, the interior of ADS. So usual black holes cap off, while supersymmetric black holes have an infinite tube. Okay, so this needs a regularization. If you naively calculate the action, it's infinite, so the contribution is 0. But this needs a regularization. Okay, so what is the regularization? So in this case, and this you have to do case by case. So in this case, sort of an early clue came from this nice observation of Hosseini, Christoph, and Zaffaroni, who said that the entropy of these black holes in question, so area of the event horizon, is can be recast as an extremization problem. Okay, so it's in particular, it's a Legendre transform of an object called I. I doesn't stand for index; it's Euclidean action, and then it's the extremum of this Legendre transform. Okay, so this is a very simple looking expression, and remember that there are only actually two independent charges, and correspondingly, there's a constraint between the three chemical potentials, which is this one: omega 1 plus omega 2 minus 2 phi is minus 2 pi I. Okay. And this reminds you of what is called the quantum statistical relation, that at least for thermal black holes, it's well understood since the 70s and 80s, that the entropy of the black hole can be recast as the on-shell action of the area space, appropriately regularized. All right? So that's useful for us, and we're going to try to do that. So let's see what happens. So if you start to do black hole thermodynamics, you write down this black hole solution, you have a temperature and some angular velocities and the gauge field. And you can measure all that, and these become the chemical potentials. And now here, if you've not seen this before, there's a small surprise for this supersymmetric black hole. So if you measure the supersymmetric values, what you find is that the temperature goes to 0. That's not a surprise. And the chemical potentials get frozen to these values, 1, 1, and 3/2. Okay. Now, this is a surprise because a priori you expect that if you want to do any kind of thermodynamics, then you want the potentials to be functions of the charges, and then you have to minimize it. Okay, so in this case, you have, these things get frozen. So these are the values independent for all black holes. Right? So that's the first surprise. And the second surprise, if you plug in these values into this relation, on the right-hand side, you don't get minus 2 pi I, you get minus 1. Right? So clearly this doesn't work as such. So what we said, this was a paper with Alejandro Cabo Bisset, Davide Cassani, and Dario Martelli, that you have to treat these solutions as limits of non-supersymmetric black holes. Okay, so you look at minimal 5-dimensional supergravity. That has a 4-parameter family of black hole solutions. Okay, so this is these are the 4 parameters, roughly corresponding to mass, charge, and 2 angular momenta. But in fact, there's actually a relation. The charges are determined in terms of these parameters in a nonlinear manner. And in this 4-parameter family, these are not supersymmetric. These are general thermal solutions. In this 4-parameter family, if you write the extremality condition, which means that the two event horizons approach each other, so the temperature goes to 0. And in this, on this surface, as I just showed, these chemical potentials get frozen. So that's a codimension 1 surface, a 3-parameter family. And then you write the supersymmetry condition, which is completely different. Okay, so the supersymmetry condition is a relation between Q and M, and it only intersects this at one point, and this is the point where the supersymmetric black hole sits. Okay, so this solution is actually a 2-parameter family, like we just said. All right. So this picture then suggests what to do. What you should do is you first go on to, since we're interested in supersymmetric index, you first go on to the supersymmetric locus. Okay, you go there. There's a 3-parameter family, and now you start varying. Now you have a variational principle. Okay, so you do that. So what you do in particular, you go away from this extremal solution, retaining supersymmetry. And what happens? The chemical potentials move away from their frozen values. This is small, this is close to infinity, and do it in such a way that this is constant. Okay, so you redefine these chemical potentials. This is roughly like the slope along this direction. Okay, and then you do thermodynamics based on these potentials. Okay, so this, I should say that this general idea of how to treat these supersymmetric black holes was first presented in a very nice paper of Pedro Silva. And then in our paper, we discussed a general formalism. There's an infinite number of directions you can take the limit in. Okay, and one of them is supersymmetric. So this wasn't spelled out earlier. And when you and then we studied that supersymmetric thermodynamics. Okay, then this was later. This formalism was used later to do also to study non-supersymmetric black holes. So you do this. Yeah, I should tell you. So what are these solutions? So in the Lorentzian theory, actually, these solutions are not physical. They have closed time-like curves. But since we want to do Euclidean theories, they're as good as anything else. And in particular, there's some complex solutions. If you take a real slice, it looks like this. It looks like some cigar. And so there's a cap. And then when you move here, it starts becoming an infinite cylinder. Okay, so this is the regularization that we were after. Now that you have this solution, you can just calculate the on-shell action. And you just, the calculation just gives you on the nose this thing that was expected. And then because this is supersymmetric, you have to demand that the Killing spinor in the bulk is regular. And when you do that, you find that that indeed you get exactly this condition that was expected. Okay, so this right-hand side is some kind of a background R-symmetric gauge field. So in the rest of the talk, I will go to the situation where omega1 equals omega2, and I'll call this 2 pi I tau. This tau will be identified with the parameter of the CFT. And when you do that, you can also solve for phi now, plug it back into this action, and you get this action. Okay, so this is something which will reappear. There's an n square. The numerator is 2 tau plus 1 cube, and the denominator is tau square. Okay, so this is the function. So what have I done? If you've sort of zoomed off for the last few pages, what I've done is I've recast the gravitational entropy of the black holes as the on-shell action of ADS space, which contains that black hole. Okay. Once I do that, because of ADS CFT, so then remember that the on-shell action is the first approximation to the gravitational path integral, and then by ADS CFT, that path integral should be equal to the index. So in this way, we've sharpened the puzzle. The index function should be exactly this. I mean, one of the saddle points should be exactly this. All right. So everything what we've done is all the questions that you could ask about the black hole entropy itself, you can recast as a question about the ADS action. Right. So this is like a change of ensemble. So in particular, this asymptotic question, this question of whether these asymptotics are correct, is completely equivalent to this question. Does the log of the index function, does it asymptote to this function? Okay, and the two limits that we discussed correspondingly have two limits. So the Cardiac limit is tau goes to 0 at fixed n, and the larger limit is n goes to infinity at fixed tau. Okay, and this is what we're going to be studying. So what I'm going to study is actually, what I'm going to tell you today is this. The Cardiac limit, I can tell you a one-line answer that you can study this limit and indeed you get this. All right, so there's some, how to do that is a technical problem. I find this a little more interesting for reasons I hope you'll see. Okay. So any questions about this so far?
Yeah, sorry, me
yes.
again.
Yeah, please interrupt, yes. Mm-hmm.
Yeah, I wanted to go back. So you had this remark that the potentials were just numbers, like when you were like, it was like 1 and 2/3.
Ah, yes.
I wanted to can we make an analogy with BTC for a moment? Because in BTC, you would also get that the angular velocity, for instance, when you're at extremality, supersymmetry is also 1. So would you say BTC falls into the same sort of?
Yeah, so ADS3 and flat space, we already have solved this problem.
I know, but that's why, but
Yeah.
potentials are also constants. Like they're not.
So this is, I'm saying that this is not some, in each case, this for supersymmetric black holes, you have to regularize it. For flat space and ADS3, it's just so well known that we don't even think about it. Okay, that's even in flat space black holes, which are, the BTC black holes are actually sitting, in the D1D5 system are sitting in asymptotic flat space.
Yeah.
You have to do the same thing. You have to
Okay.
regularize it. And you can do it in different ways. You can either keep an ADS3. The question is, what regularization is allowed with a given boundary condition, right? So BTZ, you can do it with ADS3 boundaries. The way, for instance, Ashok Sen does it, you keep only the ADS2 boundary. Okay, yeah. So in each case, there is a certain ensemble. And the question here was, can you do it while preserving the ADS5 boundary conditions? Because the danger is when you try to do this regularization, you might lose, so you might wash away the information about the asymptotics. If you do that, then I couldn't have posed this as an ADS5 CFT4 problem. So that's the problem I've solved.
I see. Okay.
Yeah?
Okay.
Okay. Other questions? So in particular, for this black hole, I can also go very near horizon and I can get some ADS2 problem. There's a microcanonical ensemble. Okay? But that doesn't sharpen this puzzle which was originally posed. And that's why we wanted to do this. And I hope, in fact, I think that we're going to hear one talk about some kind of near horizon geometry of these black holes. I forget, it's either Kevin or Vishnu, one of them, I think is going to talk in this conference. Suresh. Okay, never mind. Suresh is not paying attention. That's okay. Let me move on. Okay, so again, sorry, am I? Yeah, I'm clearly audible because Alejandra is asking the questions.
Sorry, I had a problem unmuting myself. Something stuck.
Okay,
My computer was hung. Sorry,
yes.
yes.
Is everything audible so far? Yeah.
Yes, it's audible.
All right. Okay. So again, I make a small remark here that the fact that the action has this form also tells you that the counting function cannot be a holomorphic modular form. This is for the experts, because remember that if you have a modular form, the tau goes to 0 behavior is 1 over tau, not 1 over tau square. It sounds like a detail, but actually it's very important. All right. Okay, so now I'm going to study.
Sorry,
yes.
Why would you have expected this to be a modular form?
No, just there's no expectation. This is because people who study modular forms think, like me, think that everything should be a modular form.
I see. Because you also very arbitrarily call that quantity tau. So
that I can make more precise, which I won't do. But this I can take as a question later. Why
okay.
there is a torus associated to this? This I can.
Okay.
Yeah. All right. Now, what I'm going to do is, well, I also said that because there's some relation. You'll see in a second. What I'm going to do is to study this, and the first thing I'm going to show you some numerical results. So here are some numerical results. So on a computer, you can't study the larger limit very effectively. You have to fix n to fix a theory and calculate the coefficients of the index. So here I've plotted the charge n versus the microcanonical index, the microcanonical entropy, log of d, right? So and then I scale up n. Okay, so n equals 2, 3, 4, and so on. I studied it up to 10. And then there is, you hit a computational, it's computationally very expensive. I only did it on my laptop. And after sort of many days of thinking about it, I managed to reduce this problem. Even this one takes about, the first 100 coefficients take the order of a day, about half a day or something to calculate, right? You can push this, but not very far. Okay, this one takes seconds or minutes. All right. So there are three things which I want you to notice here. One, so there's the solid line here is the prediction of gravity. All right, so that's the black hole entropy. There are three things I want you to notice. The first one is that there's such a remarkable agreement. Okay, this is up to 100, but we know that by experience that 100 is pretty large. Okay, so there's a very these dots really fall onto this line, especially as n becomes larger. Okay. The second thing I want you to notice is the fact that they sort of oscillate around some kind of a line, and this oscillation becomes sharper and sharper as you go. Here you can see it very clearly. Right? This is a phenomenon which can be explained, but I won't do it today. If you have questions, I'll point you to Alejandro, who's sitting in the audience, and can tell you about this. And the third thing, which I will tell you about, this is very interesting, is that it's, again, this is not visible in the first few, but it's very clear here, is that it takes a while before it latches on. So these dots are the microscopic answer. They sort of do something else before then latching onto the black hole curve. Okay, that I will explain at the very end. Okay, so the next 15 minutes or so, I'll explain the growth, and then at the end, I'll explain this low charge behavior. Any questions about this plot? All right, so I want to analyze this matrix model. How do we do this? So the standard technology is you first reduce it to reduce the matrix to eigenvalues. These eigenvalues, because U is unitary, live on a circle, and I'll call this e to the 2 pi I ui. So small u lives on a line 0 to 1. Okay, this d small u is the flat measure, and as usual, when you change the measure from the Haar measure to the flat measure, you get some van der Monde type object, which is a two-particle interaction. The whole potential is already a two-particle interaction because it's a double trace. So the whole index, it looks like this. It's an integral over this eigenvalues of some action, and the action is a purely two-particle action, right? Which depends only on the difference ui minus uj. Okay, so all particles interact with each other. Now, I should say that let me sort of give you an intuition of why there should be a puzzle. So if you have eigenvalues on a circle, n eigenvalues on a circle, and they have only a mutual interaction, either repulsion or let's say repulsion between every two of them, then the only sort of generic solution you can think about is a uniform distribution, or when all of them are at one point, if it's attractive. That's singular. Let's look at the other one where they're sort of uniformly distributed. Right? So if you have uniform distribution, then you can just calculate what its action is, and this is what people did, and you find that the action is actually 0, meaning it's O of 1 as n scales to infinity. Okay, so this is one of the reasons why there was a puzzle. How else? What other solution can you expect where you don't get this solution, this distribution? Okay, and our answer is that you have complex solutions. Right? So here is the U plane. So this is 0, 1, and here I've put this tau parameter, and in the rest of the talk, this is supposed to denote a lattice. So 1 and tau are the generators of the lattice, and the claim is that the eigenvalues can distribute themselves along this line between 0 and tau. So in the eigenvalue space, this was the original circle. This is the new circle. Okay, and I've sort of made it look like a torus, and that's because it will be. So what I'm going to say is that there's this lattice here, and there's a family of saddle points for every lattice point. So m comma n in z comma in z2. There is m tau plus n is a saddle point. Okay, so there's 0, 1. This is 1, 0. This is 1, 1, and so on. Okay, and when you calculate the entropy, this one has the entropy of pure ADS, and this one has the entropy of the ADS5 black hole on the nose. And then there are many other saddles. Right? The way I'm going to do this is, so first I start with this lemma. So suppose you have a potential, which is, suppose you have an action of purely two particle, and the potential is periodic. So it's even and it's periodic. And it's periodic with some period t, which can be complex. Then the lemma, the two parts, is that firstly, the uniform distribution along the period, okay, is a solution of the saddle point. You want to study the saddle point equations, okay, because we are at large n, you can study the saddle point equations. So the statement is that the uniform distribution along the period is a solution of the variational equations. That's very easy to verify. I just gave you the intuition earlier. It's a two-line calculation. And the second part of the lemma is also not difficult, that the action of this distribution is the average value of the potential along that period. This is not completely obvious, but it's a three-line calculation. Okay, you can just do this. This is not at large n. This is for any n. This is true. We're going to use it at large n. Right? So we want to use this lemma. This you can verify. It's an exercise. You can verify very easily. We want to use this to our problem. And in our problem, the idea is that we're going to sort of extend the potential away from this real line onto the complex plane in such a way that it's also periodic in tau. So there's some double periodicity, and there's a torus which is appearing, and therefore any lattice point, or in other words, some winding configuration of eigenvalues is a saddle. Okay. Now there's a third thing to verify. This extension that we're going to make is not going to be meromorphic in the eigenvalue coordinate u, and therefore, although you found a saddle point, you have to still argue why that saddle point is equal to the original integral. Why can you do a contour deformation? That needs a separate argument, which we wrote in the paper. So roughly speaking, at the beginning, at the end of the path, the sort of doubly periodic extension that we do equals a certain meromorphic function, and then you can use the meromorphicity to do the contour deformation at large. Okay, so all this is spelled out in the paper. Okay, so now I want to explain some details of this. So firstly, so let's look at this index. Okay, so this index has some explicit form. You can write it in terms of these elliptic gamma functions. All right. And here you see this is for n equal to 4 super mils. This is the vector. Oops. This one is the vector multiplet, and these are the 3 chiral multiplets. Okay. Now this elliptic gamma function as a there are only uij in the argument. Now this has a periodicity in the horizontal direction, so z goes to z plus 1, but in fact it's not periodic as z goes to z plus tau. It's only quasi-periodic, and quasi-periodic means that in this case that it's equal up to this factor of theta naught. What is theta naught? Theta naught is the usual Jacobi odd theta function divided by the eta function, right? So in what I'm going to say next, so there's this lattice, like I said, 1 and tau, and any complex number z I'm going to write as I'm going to decompose in this basis, z1 plus tau z2. Okay, and so we have some function which is quasi-elliptic, and we want to somehow change that to make it deform that, to make an elliptic function. I'm going to use elliptic to just mean doubly periodic. This will not be meromorphic. So it's a bit of abuse of terminology, which has already been done in the literature. So let's do an example. So in fact, the theta function itself, the Jacobi theta naught, itself is quasi-periodic. So it's periodic in this direction, and it's not periodic in this direction. If you go along this direction, it picks up e to the 2 pi z. Okay. So how do you fix that? What you do is you construct this function called p, which is you dress this theta naught with q to the half of the Bernoulli polynomial. Q is e to the 2 pi tau. This second Bernoulli polynomial. And then the statement is the following. So the first statement is that if you remove this constant term, q to the minus 1/12, on the real axis, p equals theta naught. That's obvious because this is only a function of z2. And notice here that I've already broken holomorphic in z. The second statement is that the absolute value of p is elliptic or doubly periodic. And that can be seen as follows. So along this direction, there's no issue. Along this direction, when you move, theta naught picks up this linear function in z in the exponent. And here in the exponent, I have a quadratic function. So the difference is a linear function, which is rigged up to cancel this. Okay. When you do that, you will find out that you actually don't cancel it completely. You cancel it up to some phase, which is independent of z. Therefore, you get this absolute value of p, which is elliptic. The third statement is that this absolute value p is actually a modular function. So this probably also partially answers Alejandro's question. This fact may or may not be clear to you. And the best proof of this actually goes back to Kronecker, who gave a formula for this function. So you take minus log of p, this is the famous Kronecker second limit formula, and you can write this. There's a limit here, and that's not at all the point of this presentation. This limit is only because in this case, the weight of this is 2. But essentially, this can be written as an infinite sum. So this, you see that in z is the elliptic variable, the periodicity is completely manifest. So this formula can be thought of as a double Fourier expansion on the lattice. And the coefficients you can see are manifestly modular. They're like Eisenstein series. Okay. So this goes back to about 100 years. And by the way, I always recommend this book. I think all of us should read this book. It's a book by André Weil called Elliptic Functions According to Eisenstein and Kronecker. So it's a very beautiful book. Now we want to do the same thing for our function. So you have this elliptic gamma function, This wasn't known until very recently. So you have this elliptic, and now you dress this up. So you put this function p to the power z2, and then in the exponent here you put the third Bernoulli polynomial and some combination of the second. Okay, so I'm going to be eventually taking absolute values, so there's no issue of branch cuts. And then the statements are the following. So firstly, when z2 is 0, you can check that q reduces to 1 over gamma. Secondly, you can check that absolute value q is elliptic, and this you can check exactly like before by checking what the difference is. And this function actually is related to this famous elliptic dialog function, which was first written down by Bloch and Wigner. I also like to make this joke. For us physicists, this is neither the Bloch nor the Wigner that we know. Okay, they're both number theorists. And now the question is there an analog of the third statement, right? Is there either modularity or is there a nice Fourier expansion? And the answer is as follows. So there is a Fourier expansion, and it goes as follows. So this log of q is not modular, but it's what is called a period function, in the sense that the lack of modularity, this should be 0 if it's modular, is not 0, but that has a very nice Fourier expansion, and that looks exactly like before. There's this Fourier expansion in both directions, and the exponent looks like an Eisenstein series. And I have a feeling we're going to see this function later, at least in Axel's talk. We're going to see something like this function. Okay, so it appears in many places. And this is this famous formula due to Bloch. There are lots of names associated. This was generalized by Ramakrishnan. And then there was a very simple elementary proof in this paper of Zaghe, which is very readable. And more recently, this kind of dressing has been discussed, and we use that. Okay. So basically, what we need is we want to sort of have some elliptic function, and we have it here. And it's very useful to have the Fourier expansion. We also have that. So you just take the imaginary part of this equation. So this one drops out. So you get tau 2 times log q, and that you just look at the imaginary part of this. So the bottom line is that we managed to write the action of the superangles in terms of elliptic functions. Okay, here I've skipped a step. I've removed the absolute values. Can discuss this later. It's quite easy. All right. So in terms of these functions log q and log p, and this is well defined on the torus, and therefore now we can use our lemma. So for every lattice point, or for every winding string of eigenvalues, you have a saddle point. And now we want to calculate the action. And now by the second part of our lemma, if you want to calculate the action between 0, when the eigenvalues stretch between 0 and m tau plus n, you just want the average value of this potential. The average value of this potential now is almost trivial to calculate because you have a double Fourier expansion. Okay, so now it's just a 3-line calculation. Right? You have a Fourier expansion along any direction. You just project it onto the direction you want, and then just read off the coefficient. Okay, so this technology is really nice. And here's the answer. So you calculate the action, you get something like this. You get an n square divided by m times this cubic function divided by a quadratic function, where here chi1 is this Dirichlet character. Okay. So in particular, this is for any m comma n. In particular, if you plug in m n equals 1, 0, you get exactly this function n squared times 2 tau plus 1 cubed divided by tau square, which is on the nose, this on-shell supergravity action. All right. Okay. Any question about this? Because I'm going to change the topic just a little bit. Maybe let me finish saying one more thing. So you see the near tau goes to 0. If you look at all these actions, this is the one that dominates. So now I have a bunch of saddle points. So I can ask the following question. Give me any tau, any value of the chemical potential. I can ask which saddle dominates. So in other words, I want to construct the phase diagram. So you can see that as tau goes to 0, it's this one that dominates. So you can indeed see tau goes to 0 is roughly like very high temperature. Of course, this is all supersymmetric. So that is being borne out. In this diagram, there's a symmetry along the central vertical axis. And so you can only look at one of them. And I've cut off tau 2 at 0.1. So when you go a little bit further, here is where tau equal to 0 lies. All right. And you can see that there is this, I don't know what, musk colored region is the black hole. And here there's an entropy of pure radius. All right, this is some sister of this black hole. All right. However, if you go back here, you'll see that as tau goes to any rational number, minus n over m, there's a new phase which dominates. It's this one. Okay. So indeed, when you pull down tau a little more, this was 0.1. If you go to 0.01, you start seeing the other ones popping up. So near any rational point, you see a new phase. And there's a rich structure of phases of this theory. Right? So there's many other things you can do now. I mean, basically, you have a lot of technology with which you can play with in the large N theory of this model. Wait, one more thing, and then I'll pause for questions. So this whole thing can be generalized for, as I said, to n equal to 1 superconformal field theory is a very general class and include flavor chemical potentials. And this was in this paper. There's a big paper. I'm going to just summarize 3 points. So the first one is that just like what I showed you, there is a universal family of saddles, m, n, with a large entropy. And universal means that in the supergravity theory, that it doesn't depend on the details of the theory except for central charges and so on. So therefore, they must have gravitational duals, and certainly the black hole exists in all theory. But in fact, there's a whole family which exists in all theories. The action of the theory, now, if you include flavor chemical potentials, delta, this bracket means something which I won't tell you now, has a very sort of elegant form. It's completely governed by anomalies. C, I, J, K are the anomaly coefficients of the flavor symmetries of the theory. And thirdly, here I showed you at large n that there is a family of saddles m, n, which is already an infinite family. But in fact, we showed that we couldn't prove that these are all the saddles, but there's a very large family of saddles. When n has divisors, so there's some number theoretic structure. When n is even, for instance, instead of the eigenvalues being uniformly distributed like that, you can have clumps of 2 eigenvalues uniformly distributed like that, and so on. And this structure is classified by finite abelian groups of order n, and then you embed them into the torus. Okay, these are just some highlights. Again, I can take questions about this if needed. Okay, so any questions about this before I go to the last point?
Yeah, me again. So, because you mentioned entropy, then it means that these other saddles, are you making a statement about the Lorentzian interpretation? Like, or are you saying that they have a large, like, complex free energy associated to them? Like, is it clear that it's entropy? Like, or are we?
So let me make the correct statement and then let me tell you what I think. The correct statement is what you said, that this is the Euclidean path integral. And it has I'm saying that there are lots of saddle points. And I'm telling you what is the value of the effective action at that saddle point that can be complex. Right? Now, what I think is that, I mean, actually, again, you know this very well. So think back about the ADS3 situation, right? The ADS3 situation, according to Maldacena and Strominger, was exactly this, that it's labeled that you have a thermal ADS, pure ADS3, you have a BTZ black hole. So this is 1, 0, and 0, 1. And you have an infinite number of black holes labeled by m, n. In the Euclidean theory, they're all complex. Okay? So I'm making exactly the analogous statement. So it's not a statement. Those Maldacena Strominger family of black holes don't have Lorentzian interpretations, as far as I know. Maybe you know better. But I think that's certainly the consensus. And it's a similar statement I'm making. One should find, except here, even in the Euclidean, we have found these solutions. So I'm making a prediction for people interested in finding gravitational solutions. There must be gravitational solutions with that much action or entropy.
Okay, I would say action so far, because as you say, for the
action,
BTC,
entropy, I just mean the real power of the action. Yeah, that's all I mean.
Okay. Yeah, but then from the field theory point of view, like maybe more similarly to like D1, D5 or something like that. Should I think of this as some like wall crossing, like the fact that one is dominating over another one?
No.
Can
No. The BTZ is the correct analog. There's no wall crossing there. Think of BTZ. There's
Yeah, so it's just like the different
It's a phase
faces, like
transition.
it's a phase transition. But but you wouldn't think of like things splitting up or like having some multi-center configuration or.
Not according to anything I've said so far. That's a story which there's. So there may be a story of that sort, and I've not given you any hint of that at all in what I said.
Okay.
I'm very happy to discuss that with you, but that's more complicated, and we only have hints. There is some hints of this. So maybe Alejandro and you and I can have a discussion later, or maybe even in public. I don't mind at all. But it's so far what I've presented has nothing to do with it.
Okay. Okay.
Yeah. Actually, I have also a question, Samir. I mean, this Dirichlet character.
So is this Albrecht?
Yeah.
Yeah. Mm-hmm.
Is this physically interpretable? I mean, why you get this Dirichlet character in this formula? Or is just how it comes out, or?
Well, this is a calculation. That's the answer. But the mod 3 is because of the quantization of the R charge of n equal to 4 super angles. Okay, at least the 3 I explained. And now these are real numbers. They're not complex or anything. So it's not. I mean, it's not super surprising.
So you're saying, okay. So
I mean, let me say it this way: when it's 0, then these solutions will not have large entropy or large action, right? Because then it doesn't go as 1 over tau square.
So there's, so basically it's just a calculation, and okay, it's a calculation.
So far it's a calculation, yeah. So there might be some more interesting way to understand this, but it's a calculation.
Okay, thanks.
I mean, from the mathematical point of view, from the calculational point of view, it's not at all surprising. I mean, these are elliptic.
Yeah.
These function.
No, I understand this part. I think I was asking for a physical explanation.
So I don't know, and this is so. I mean, let me ask. I mean, at the end, I'm going to pose another question. Like, is there? Let's wait until the end.
Okay.
All right. Other questions? Okay. It says 1 hour in my clock. Can I just continue for? I had another 5 or 7 minutes. But
go ahead.
It's fine.
Okay. Okay. Now comes this last point. After this original paper of Kinney, Maldacena, Minwala, and Raju, people started to take this seriously and say, well, let's try to look at this numerically. Can we understand why there is no growth, or as it was thought then? Right? Now, so here's one explanation that was given, namely that at n equal to infinity, we know that single trace gauge invariant operators in superangles theory for low charges are single gravitons. Okay, this is basic area CFT. Now you can ask what happens to the multi-trace. So in the formula, you're supposed to count all multi-trace operators as well. Right? So you can ask what happens to multi-trace BPS operators. So certainly some of them are multi-gravitons, because you have single gravitons, you can put them together, and those will be BPS. The question was, are they all multi-gravitons, or are they something else? Okay. And this question was actually sharpened in this very nice paper by Chang and Yin. And they showed that this is a fact, that, this second line, that at infinite n, it is in a very precise sense, if you look at the Q cohomology, all the Yang-Mills BPS multitrace operators are or can be written as multi-gravitons if you use the ADS CFT dictionary. Okay, and then numerically the checklist to the first few orders. Now this looks to be in complete contradiction with what I've been saying so far, right? That for there should be a growth of these number of operators. The graviton entropy of the gravitons lives somewhere here. It's very, very small compared to here. There is no growth at all in large N, okay, in the gauge group, rank of the gauge group. Okay, so how do you resolve this tension? And so I've given all the language and all the hints needed to resolve it. Part of the issue was to clean it up a little bit like that, and it has to do with what regime of charges you're looking for. All right. The answer is that this index function, the index itself, now I mean the microcanonical index, interpolates between multigravitons and black holes. So this statement that n equal to infinity, the multitrace BPS operators are multigravitons, when you want to put it on a computer, n is 10 or 100 or something, then you have to say, what does it mean that 10 should be thought of as infinity? What it means is that there's a regime of charges beyond which this statement doesn't apply. And that's exactly what happens, right? So what you see here, and this you can quantify. So here is, this was in this paper of May. So this is the charge, the horizontal axis. And here I've shown you the index for ranks 2, 3, 4, 5, 6 is UN, okay, 6 and so on. The last line is the graviton index. You see exactly when the, I should get this correct, when the charge equals 2 times rank plus 1. Okay, so here 5, 7, 9, etc. Until then, the index is precisely equal to the graviton index. Okay, right? And then it starts to deviate. Okay, so there's no puzzle. So basically the point was, if you look large enough, you'll start to see, numerically you'll start to see the deviation. It's very interesting. So here's a graph. So this red plot is the graviton index. Okay, right, horizontal axis is the charge. This is the entropy. So that's the graviton entropy. Very close to this, you can't see this in the plot. Very close to this, the graviton entropy actually latches on, sorry, the index entropy actually latches on to the graviton. So index latches onto the graviton index. Okay, you can see this here, but it's clear in the tables. Then what happens is there's a little bit of a dip. Okay, you see that? And then after that, it zooms out. Okay, it zooms out here. Okay, and then this starts growing towards the black hole entropy. So here, these numbers are confusing. So if you just did numerics up to 20, you'll be confused. You would say, you see that these numbers are smaller than the graviton, right? But then you should remember that this, what I showed you here, is just the first 100. And that's sitting somewhere over here. I've shown 100,000 is sitting somewhere here in this graph. Okay, so there's absolutely no puzzle. There's a very beautiful interpolating function which does everything it's being asked to do, okay, according to all our ADS-CFT principles. And this fact, this observation that I made, can actually be proved. Okay, that's what I did in this paper as follows. This is my last slide. And this, I'm quite excited about what I'm going to say next because it points to something else. So here's the proof. You start with this index formula as an integral over the UN matrices. There's an exponential. Everything has a U in it. You expand the exponential. That exponential, every term then will be of this form. There'll be some trace U to some power to some other power times trace U dagger to some power to some power. Okay, so a generic term will look like this. Okay. Now what you do is you expand such traces, multi-traces, in characters of U. Okay, this is the famous Frobenius formula. So how to do this? For every such multi-trace operator, notice that it has a cycle structure. Okay, so here's a partition P. So this, you think of this as a J cycle, and then you have Kj copies of this. So this is like 1 to the K1, 2 to the K2, etc. So it's really like a partition. That partition can be written as a sum over characters of UN, that's that, chi tilde, which are also labeled by partitions, as famously known, which is lambda. And the coefficients are precisely the characters of the symmetric group. Okay? And this sum goes over all partitions whose length, which are allowed by UN, which means that the length, the number of rows in the Young tableau has to be less than or equal to n. Okay, that's the labeling, that's the character lambda. Okay, start with this. You write a similar formula for U dagger, you put it together, you integrate over U. Integrate over U, you have chi tilde lambda times chi tilde lambda prime with U dagger. So you have the second character relation. So that first character relation, so integral over U gives a delta function. So the whole thing, you can now collapse this to sum over partitions. Okay, so it's a double sum over partitions over P, and this other partition lambda. Okay, and here this function IS. Okay, so it's sort of the function to some power. Now, so here is the restriction that the length of the partition lambda should be less than or equal to n. As n goes to infinity, this is trivial. This doesn't mean anything because you sum over all partitions. If you sum over all partitions, you have the second character relation, which say orthogonality relation, which says that this object is equal to 1. So that drops out, and you just get a sum over partitions of this function IS, which is easily seen to be just some infinite product. Okay, this infinite product is precisely the multi-graviton index. This you can show very easily. And this whole proof, you can, if you sort of now run over it again with a fine comb, you can see that this whole thing goes through. If you want a Fourier coefficient of this, the whole thing goes through as long as the charge is less than or equal to 2 times rank plus 1. Okay, that's because long ago I showed you what IS is. It starts with 2. That's why you get a 2n. Okay, so I just want to give you a flavor of this. So let me end with these outlook and questions. So these are things which I think are important. There are many things I skipped. So firstly, complex saddles are important. There are many phases we already discussed a little bit. There seems to be this lattice. So there is no modular symmetry, but there is some hint of underlying modular symmetry. There are these period functions, which is well-known theory in modular forms. Physics-wise, can we understand this elliptic deformation? My best guess is that it should be a Q exact term. That would be nice. The fact that I could write the Yang-Mills theory as this index as a sum over partitions with some random partitions, this looks like two-dimensional gauge theory. And there's a very rich story, right? There's a phase transition, Douglas-Kazakov phase transition and so on. So this is suggesting some story of that sort. And finally, this is the question which I was mentioning to Albrecht, that is there a reason why these functions appear? Now, in mathematics, these functions were introduced for some very deep reasons. They have to do with algebraic K-theory, and more lowbrow reason is that the values of these functions have to do with L function values. That's something that most people here can understand. And the question is, can we sort of really relate that to super Yang-Mills theory? That would be really wonderful. All right. So I'll end here. Thank you very much.
Thank you. Right. Thank you very much, Samir. It was a very nice talk. Are there any questions?
Maybe I can ask
I have a question to the last point.
This is Sergey.
Oh, sorry. I'll wait.
Okay, sorry. This is Sergey. Samir, can you explain what do you mean by tau to minus 1 versus tau to minus 2 period functions?
Sorry, tau to minus 1 versus what?
It's on this slide.
Here is 1 over tau versus 1 over tau square. This is, I just say that modular forms, holomorphic modular forms which have growth, near tau goes to 0, like take 1 over eta or something like that. That goes as 1 over tau, e to the minus 1 over tau, right? Sergey?
Yeah. Yes.
Right? I mean, this is the standard Cardy formula. If you take 1 over eta to 1 over eta, and you ask, what is the behavior of the function as tau goes to 0? Right? It's e to the 1 over tau.
Yeah, and in your case, it's different.
In my case, it's the action versus 1 over tau square, right? And what is happening is that, let me explain that a little bit, the technicality of that. So I'm happy you picked up on that. So technically, you can see this from this function. So this, if it's a modular form, this should be 0. If it's not, so here it's not 0. The right-hand side f is itself this kind of, Eisenstein type series. This is E1, 2. And now notice that there's a tau here. Okay, so if I want to estimate log of Q, there'll be a 1 over tau in addition to this. And that's the reason why you get a 1 over tau square. Is that clear?
Yeah, so you say that this is a crucial difference from the usual modular.
Yeah, I mean, in some sense, maybe I'm overemphasizing something. It's just that I was looking for entropy, and I said, well, let's look whether this thing should be, is there some modular form behind it? And then once I realized that the gravity tells you that it should be 1 over tau square, I immediately gave up looking for modular forms because it can't be. So the nice surprise was that somehow there's some modular form which comes in the background.
And in this, equation which...
I don't think it's a deep point, but I think if you look to measure entropy, it's important.
And in this equation, which you just pointed out...
the block formula. Mm-hmm.
Yeah, so it looks like it's a kind of anomaly equation, yeah, because there is a...
Sorry, I should have stayed there. Anomaly.
I mean, can I see this F like something like an anomaly? Or
No, this is exactly what the theory of period functions is. Albrecht can explain this. He explained this to me once, so I think he's the best person to ask this. Right? It's a fact that this thing can be written as a period. There's some integral between 0 and infinity. Sorry, many people know about this, and I don't mean Boris.
actually, my question was: is it related in any way to mock modular stuff?
Not that I know. I mean, there is. So the only thing I can say is the following. So the answer is no. But then maybe at some structural level, a higher structural level, let me make a comment. So maybe you've heard Zagier give these talks where he writes a lot of different types of functions, and he wants to give a name to these things. I don't know if he's come up with a name, but basically the point is these functions have a relation between how they behave in the upper half plane in tau and how they behave in the lower half plane. And the relation is that there's some kind of a leakage at all rational points. Do you know what I'm talking about? If not, then we'll discuss this later.
Okay.
If not, then let's discuss this later. But roughly, this belongs to that class of functions. Mock modular forms also belong to that class of functions.
Okay, thanks.
Yeah. But there is no sort of mock behavior to Q or anything of the sort.
Okay.
I wanted to ask you, maybe,
Yeah.
are there Hecke L functions coming up already, or I mean?
Well, so that's a great question. So this was my last thing. So you know that the value of these are precisely related to the values of the Hecke L functions, right?
Right.
So what your question is can I calculate them physically? And I don't know. We should discuss this. That will be really fantastic.
I see.
You're asking if there's a physical reason for it. Actually, before that, even there's another question which I think isn't. We should absolutely discuss it. But even before a reason, can we sort of find a physical observable whose answer is that? Even I think.
Yeah. That's what I'm more or less asking you.
Yeah.
Okay, good then. I think. Thank you for the beautiful talk.
Thanks.
Very much.
I can't hear you. Yeah.
Well, mute your mic.
Well,
Go.
So I should stop sharing, right? Here you go.
that's right. Yeah.
Wait, where is this now? Here.
All right.
Thanks, Amir.
Thanks.
Sorry, Samir. I think Sergey has one more question.
Yeah, but we can do it like this. That's okay. I don't need to share screen. Question.
Sorry. What did you say?
Abiram, did you have a question?
No, it's just a clap.
Oh, I see.
It's not the ask question feature.
All right. Okay. So we'll continue now with Axel Kleinschmidt.
Yes, hello. So let me
Hi.
first try to share my screen as well. Let's see if it works.
And then I'll briefly introduce you.
Yeah.
Is this full screen?
Can you see this?
Yeah, but you should go full screen.
It's full screen for me, but okay.
Okay, all right. Okay.
No, but then let me try something else because I've had this issue before. So let me first go full screen and then share. That helps. Let's see. No, that doesn't work. What do you see now?
Yeah.
Okay, good.
Very good, very good. Okay, so now we have Axel Kleinschmidt from the Albert Einstein Institute. Axel will talk about innate BPS couplings in effective string theory. Thanks very much. Thanks. Go ahead.
Thank you very much, and thank you for the invitation to speak. So indeed, I'm slightly more supersymmetric than Samir, 1/8 instead of 1/16. And I should also say that I'm not going to show the formula that Samir mentioned, this E1, 2 kind of modular form, but some other modular forms or automorphic forms. The talk is about joint work that I did with Guillaume Bossard and Boris Piolin, who's in the audience, earlier this year. And it has got to do with certain specific terms in the string theory effective action. And since I wasn't completely clear, sure what the audience would be, I have a slightly gentle introduction into what the actual thing is that we're computing, because the computation is quite technical. And so one thing that we're all familiar with is that if you take the type 2 string and you put it, say, on a torus, you take the alpha prime to 0 limit to go to low energies, what you end up with is maximal supergravity in this compactified dimension d, 11 minus d. And this maximal supergravity theory has a global continuous ED symmetry, and it's the effective action. And it's the point that I want to emphasize. It's the complete low energy effective action in the sense that it has information both about the perturbative properties of the string, but also about the non-perturbative properties in the sense that it contains the brane solutions as field theory solutions. This is the strict alpha prime to 0 limit. Of course, string theory induces alpha prime corrections to supergravity. So these are of the form that they are higher derivative corrections, let's say Riemann to the 4th power. They come with a dimensional full coupling, the string length to some power. And generically, if we're in this compactified situation, there is a coefficient function that depends on the moduli of the theory. So in this case, the global symmetry was ED. And the moduli space is well known to be just ED over its maximal compact subgroup. And the moduli, the coefficient function here depends on these moduli. So this is the kind of what I would call a higher derivative coupling, and similar things will be the main features of the talk. One thing that you notice immediately is that once you turn on these high derivative couplings, the continuous symmetry that you had in supergravity is broken to a discrete symmetry at most, namely this stringish U-duality, which is ED over the integers and not over the real numbers. And I want to say like a few words about these effective actions. So they're effective actions, which means they're designed to capture the interactions of the string up to a given order in alpha primed. And let's look at this, for example, for 4 gravitons. So if you compute a 4 graviton amplitude at tree level for very low values of alpha primed, this is the string scale. So you're basically doing a field theory calculation, and this is what the supergravity lower energy effective action does. And in this field theory picture, where you only have field theory degrees of freedom, this term here actually corresponds to the exchange of massive string states that you integrate out. So you get some effective new interaction vertices from the field theory point of view, which is a new coupling in the effective action. And this would be, I mean, for any order in alpha primed, you would generate new couplings that you have to add to your effective action. So it's in general very hard to determine these coefficient functions of the moduli f of phi. And this is where all the information about the string loop order and the background that you're actually doing the string calculation on is sitting. So this is hard to fix, and this is what I will talk about, how to fix some of these. And of course, I will make some references because this is an old topic as I go along. So there are 2 ways that I would like to mention here, how you can determine these functions. So these will be the main players. One thing is similar to what I just showed you. You can just do a direct calculation of some aspects of this function using the perturbative string, like a tree level 1 loop amplitude and so on. So this is why the S here is in a different color. You have to do infinitely many string calculations to get all information about this function. So this is clearly something that gives you some glimpses of the function, but it's not enough to fix it completely. And to fix it completely, in some cases, you can use indirect methods, namely just using symmetry arguments and maybe mapping it to some auxiliary system so that you can fix this coefficient function. And this is this second route is particularly feasible when the coupling here has some residual supersymmetry or it has some BPS protection. And as you can guess from the title of the talk, this will be the situation that I'm in. Let me just give you a few more words on the first point here. So the direct calculation is, for example, when you take this 4 graviton kind of interaction in 10 dimensions at tree level, the amplitude, the perturbative string amplitude has been known for a long time, and takes this form as a ratio of gamma functions. And then there's some overall thing that I write as r to the 4 because it corresponds to the kinematic structure of this, and it absorbs the polarization of the gravitons and other things. It's a function that only depends on the Mandelstam variables, and then there's an overall prefactor which corresponds to the fact that we're at string tree level. So, so in what way does this teach us anything about this function? What you have to do is you have to do an expansion in alpha prime to see this, these aspects here. And if you just expand these gamma functions in alpha prime, this is what you generate. So you generate certain zeta values to zeta 3, zeta 5. And these are the terms that go into the effective action. So if you convert this answer here, which was in string frame, into Einstein frame, this means that this r to the 4 curvature correction that I'm writing here, for example, this f of the corresponding coefficient function has to contain a term which is 2 zeta 3 times this power of the string coupling. And keep in mind that, I mean, here the phi in general are all the moduli. So one of the moduli is the dilaton, which is related to the string coupling. So this is really a function of this capital phi. And the next value here corresponds to a new correction term, which is higher order in derivatives, because it has more powers of alpha prime. So this is how you would do direct calculations of these coefficient functions, or at least parts of these coefficient functions. And they're really only part because this was just a tree level calculation. And in principle, you would want to go on and compute 1 loop, 2 loop, and maybe even some instanton calculations to get the full function. And here we have a closed formula in alpha primed. And I should also mention, which is probably known to most people, that this is the only case where a closed formula in alpha primed is known. If you, as soon as you go to string loop amplitudes, there are no closed formulas in alpha prime that I'm aware of. So what people do is they just really do perturbative calculations in alpha primes to get these coefficients or the analogs of this coefficient at loop order. And this is where these Eisenstein series and modular graph functions would come in. But this is not what I want to talk about today. So please interrupt me at any moment. So I want to just go on and be a bit more systematic about these higher derivative corrections, because I will talk about different ones of them. So I'll introduce some systematic notation. Here, this is just the part that corresponds to supergravity. This is the 2 derivative action. And these are just the moduli scalar fields. And then I'll be interested in the first 3 corrections for gravitons. So this would be the r to the 4 that we just saw. Then there's a higher derivative term, which is d to the 4, r to the 4. And this is d to the 6, r to the 4. And I'll give them specific names that will keep coming up throughout the talk. The moduli fields, as I said, they include the string coupling, but they also include other information about the background, like the shape of the torus, the form of the torus, and also the Ramond background fields. And these functions, they are quite complicated, but we know that if you expand them out for a small coupling, for example, they must reproduce what we just saw for the tree level calculation. So this was the direct calculation we saw on the previous slide. And these functions, this is the one for r to the 4, this should reproduce the same value. And here I'm writing this for the type 2b case where the moduli, the modulus is just the axial dilaton. So this is the Ramond axion with a string coupling from the dilaton. And this is when you expand this function of capital phi for small coupling, this is what you should see. And you should see many other things corresponding to the other calculations. Good. This is what I wanted to say about the direct way of looking at these coefficient functions. So these are really the things that determine how string theory corrects gravity. And now I want to talk about the indirect determination. And for this, you might have wondered what was the particular reason for why I labeled these functions with these particular subscripts. And the systematics here is that if you have certain polynomials in the Mandelstam variables with exponents p and q, and as long as you have massless states, everything can be reduced to these two invariants. This is where these labels come from. So very generically, we're in context on the torus where you have U-duality, which means these coefficient functions have to be invariant under U-duality. So gamma here is an element of the U-duality group. Acting on the moduli, it shouldn't change the function. And since we're in a symmetric space, everything only depends on E divided by its maximum compact subgroup. It also has to be invariant under right multiplication by K. And now the point is that this U-duality, of course, includes S-duality, which relates strong to weak coupling. So this means that this function here that we are looking for, or that we're discussing, contains all perturbative and also the non-perturbative, the strong coupling physics of the string scattering amplitude. And this is, as I was saying, this is something that has been done for many years. And here's a list of the main contributors. And this is why these are such interesting functions, because they also contain things about d-instantons and d-instanton combinatorics and things like that. So the first few of these coefficient functions, they are BPS protected. So the first one is half BPS, which is r to the 4. The next one, d to the 4, r to the 4 is quarter BPS. And then there's this 1/8 BPS function, which is at the order d to the 6, r to the 4. And this BPS protection means that when you compute the string amplitude, there are only very specific string states that can contribute to this amplitude. So not all the non-BPS states of string theory contribute because of zero-mode saturations. Only very specific terms can contribute. And this is one way of saying what the BPS protection is. Another consequence of that is that these functions are functions on this moduli space, functions of phi, and they actually satisfy very restrictive partial differential equations with respect to phi.
Sorry, Axel, can I ask a question?
Yes, please.
So is this a perturbative statement when you say that it's BPS protected? I mean,
no, this is a non-perturbative statement.
So I'm confused. You said you mentioned string amplitudes.
Yeah. So yeah. So let me maybe go back to this slide here. So this is a function of all the moduli, which is a function of the full axial dilaton, for example. Mm-hmm. And string amplitudes. I mean, you can do perturbative string amplitudes like free level 1 loop and so on over Riemann surfaces. To get this full non-perturbative function, so I'm really saying something non-perturbative here, you will also have to do string scattering calculations in an instanton background.
I see. Okay, thanks.
So this is where the non-perturbative thing comes from. Yeah.
Thanks.
Are there other questions? Okay. So, so these are very special functions, and they've been looked at a lot in the literature. In particular, the first two, which have a lot of supersymmetry left, they have been determined over the years completely. And this last one hasn't been so clear how to determine it for all possible toroidal compactifications. And this is the issue that we clarified in this paper with Guillaume and Boris.
Axel, can I ask you?
Please.
Does it mean that there are no, these functions E with high labels, they are not all not protected?
So yeah, so if you have higher labels than these ones here, I think the general expectation would be that they're not BPS protected. I think, well, the default assumption would be that this means that they don't satisfy very special properties, although this is something that has not been really investigated so much, but they're not BPS protected anymore.
So there is a little hope to find them.
There's little hope. I mean, so there have been some papers where people looked at the next one, which would be d to the 8 r to the 4, which is non-BPS. And depending on which papers you look at, some people say that there should be partial differential equations still, which are weaker than the ones for the 1/8 BPS, but still some equations to constrain the couplings, and other papers say these couplings are completely unconstrained from this point of view. Of course, they still have to be U-duality invariant, but some of these differential equations, they're really important for pinning down the automorphic function that you're looking for.
Okay,
So yeah, I think it's the safe assumption would be that the higher ones are completely non-BPS and they're not very constrained. And to construct them fully, I think there's not so much hope.
Thanks.
Okay. So yeah, so somehow these properties here, there are sufficient or almost sufficient in the cases that I've shown where you have BPS protection to determine the function, this very complicated function, almost completely. So you, in some sense, you don't have to do any of these perturbative string calculations or not too many of these perturbative string calculations. And you can just immediately, by looking at the right space of functions and the differential equations, say what this function must be. And this is what has been done. So, and I will want to describe a slightly different way of doing this, which exploits more heavily the fact that here you have this very particular set of states that can only contribute. So this is something that I would refer to as BPS enhanced field theory. So somehow the fact that these couplings are protected means that you don't have to study all of string theory if you want to understand these couplings. So you only have to look at very specific string states with a certain remaining supersymmetry. And this means you can actually do a calculation not in string theory, but in field theory, which includes these additional states. So this is why I call it BPS enhanced field theory. It's not just only supergravity, but it's supergravity embellished with very specific BPS states. And this is an approach that also has been taken to compute these functions in 10 dimensions using supergravity field theory calculations to determine this one here is the R to the 4, and this is the D4 R to the 4, so the half BPS and quarter BPS 10-dimensional coefficient functions. And a similar work actually was done slightly later by De Witt and Lust for 9 dimensions, I think. So what is this BPS enhanced field theory that I will use in the talk? So what we want to have is we want to have manifest U-duality invariance. So we're looking for a formalism that has this ED symmetry somehow built in, because these BPS states, clearly they respect U-duality invariance. So you can map a momentum BPS solution to a brane solution and things like that. So we want to have a formalism that has this built in, and the formalism that relies on this exceptional symmetry groups is called exceptional field theory. So I will be using loop calculations, not in supergravity, but in this extended or BPS enhanced field theory, which is called exceptional field theory. And for those of you who have been in touch or have been to talks on exceptional field theory, they might remember that something that is very important in exceptional field theory is that they satisfy something called the strong constraint or section constraint. And this, as we will see more clearly in a few minutes, is related to what is known as the half, or what is exactly the half BPS constraint. So this relates to the fact that this exceptional field theory is somehow supergravity enhanced by all the half BPS states, at least in the way that I will use it. Okay. Yeah, I'm not sure how familiar people are with this idea.
I can interrupt once more, sorry.
Sure, please.
So what are these states physically? Are they deep branes or are they massive string states, or what are you talking about?
So, well, I will give you an example in a second, but for example, if you take, let's say you take 11-dimensional supergravity, you compactify it on a torus to a lower dimension, you have Kaluza-Klein BPS momentum states. And which, I mean, just wrapping like the graviton on this torus, but by U-duality, this gets mapped to certain brane states that can also be wrapped on the torus. So it's really just the BPSD branes, yeah. Or membranes, depending on which frame you look at.
All right, thanks.
Okay, so yeah, I wanted to give you a very short idea of what this exceptional field theory is, which is a formalism to make this ED symmetry manifest, and manifest in a geometric way, where geometry here is put in inverted commas because I mean, I think differential geometrists would not call this a geometry, but it's something that makes sense locally in the sense that you have Lie derivatives and gauge transformations. So you want to, this formalism makes this geometric in the way that it combines the usual gravitational diffeomorphisms together with the gauge transformation of all the matter fields into one geometric structure. And the way that this works is that you work on an extended space time. There's an an external space time, d-dimensional, which is the non, let's say, usually it would be referred to as the uncompactified dimensions. And then instead of the usual compactified dimensions, you take an extended internal space. So you take a space and you want to have manifest ED symmetry. That means that this space somehow must carry an action of ED. So it's much larger because its dimension here is labeled by a certain irreducible representation of this exceptional symmetry group. And here I've said it's the highest weight representation on node alpha D. So on the dth node of this diagram up here of the exceptional symmetry group. So this number d alpha d, the dimension of this representation, is bigger than little d. And so this is really, you take the usual, let's say when you go from 11 to 4, normally you would have 7 internal directions. You make it much larger. In this case, it would be 56 dimensional. I will give you a table in a moment. So you work on this sort of extended space-time. And for the purpose, and you formulate the theory here, I will not go through the details of that because what I will use here in this talk is that we assume this extended internal space is toroidal. So that means that instead of that all the momenta on this space are quantized, so I can write down a momentum vector, let's say gamma m here. And this is something that lives in a lattice of the same dimension as the space. And if you take this lattice, which is a lattice within this representation on node alpha d, you can take that representation and branch it out to, let's say, GLD, which would be, if you're in E7, this would be GL7. This is more like the usual 7-dimensional internal space that you're more familiar with from Kaluza-Klein reductions. If you do this branching of this representation, these quantized momenta on this extended space will decompose in the following way. So there will be, as I said a moment ago to Samir's question, Kaluza-Klein momenta, but there will be also additional things that are like wrappings of M2 branes, M5 branes, and if you go very low, you also get wrappings of Kaluza-Klein branes or monopoles. And yeah, so somehow this is something that transforms nicely under this exceptional symmetry group because it's a representation, and this is just the statement that half BPS states in this compactified theory, like the branes, they form U-duality orbits, and these are the things that go together in a single U-duality orbit. So from our point of view here, what this means is that these quantized momenta you can think of as charges of BPS states. So if you really wanted to look at a half BPS Kaluza-Klein momentum or wave, you would just turn on one of these things in a specific direction, put the other ones to 0, and this would be the charge of a BPS state. But in general, I mean, you can have other charge configurations. I mentioned a moment ago that exceptional field theory very importantly has this section constraint, and this section constraint in the standard formulation of exceptional field theory is there to close the algebra of local symmetries, so of the gauge algebra of these generalized diffeomorphisms. And it's typically written in terms of a product of derivatives has to satisfy certain properties. Here I've written it in terms of these quantized momenta. So the product of two momenta projected to some other representation of this exceptional symmetry group has to vanish. This is this section constraint. And here I've written out for you for a few cases what the corresponding representations are. So this is the representation where the momenta would live, these quantized momenta. I said a moment ago, E7 would be 56. And this representation of the section constraint in that case would be saying that if you take two vectors in the 56, their product restricted to this 133 adjoint of E7 has to be 0. So this is a certain representation theoretic constraint on these momenta. And when I say it in this way, it's maybe something that is not so familiar to many people. So let me give you the form that you get for this constraint when you write it out in terms of the individual Kaluza-Klein brane, M brane, M2 brane, and 5 brane charges. So writing out this constraint here in this branching that I had on the last slide, it takes the following form. So it's just this is the 2 brane charge, the Kaluza-Klein momentum charge. This is the 5 brane charge. So there are certain relations that you have to satisfy among these charges. And this maybe is a form that is more familiar to some people because these conditions here are nothing but the conditions for the charges of this object. So if you compute them using some, I don't know, ADM or some kind of formalism like this, this is the condition for the charges to be half BPS. Whenever you satisfy this list of constraints, the corresponding charge vectors are half BPS. So one way of solving these constraints, for instance, is if you only turn on the Kaluza-Klein momentum direction, you see everything here then vanishes because it contains at least one of the other charges that are set to 0. So this would be one way of solving it. This is called the M-theory solution, or just looking at a BPS state, which is a pure Kaluza-Klein momentum. But of course, once you have one solution, you can use U-duality to move it around, so you will have many solutions. And really the important point is that this constraint here that I will abbreviate as just gamma cross gamma equal to 0, this is nothing but the half BPS constraint for these charged objects. So this is a setup that has built-in U-duality, so it has the built-in symmetry that we want for the coefficient functions. And now we want to use this setup to compute amplitudes, because this is what should teach us about these BPS protected couplings in the string theory effective action. And now what would an amplitude in this setup look like? Let's look, for example, at a one loop amplitude with 4 gravitons. So relying on some results from supergravity amplitude calculations, it's known that this kind of amplitude should reduce to a scalar box diagram, where you can factor out the polarization part again, and then you just have a scalar, one loop scalar amplitude, which I've written out here. And now the point is that we're in this exceptional field theory context. So the things that can run around in the loop are both the usual external momentum P, which you integrate over the loop momentum, but it can also, you can also circulate these BPS states in the loop. So this is where this BPS enhancement of the field theory calculation comes in. You have additional states that can run around in the loop, and you have a full U-duality multiplet of states that can run around, and I impose that these states have to be half BPS. And then you have the usual, I mean, there are 4 propagators here, so this is the usual Feynman rules for this thing. And of course, now from these BPS states that can run around in the loop, you also have to get some contribution to the propagator. So you just get something that looks like a mass from the external point of view. And this mass is just the BPS mass of the BPS state. And it depends, that I write here, C of gamma squared. And it depends on where you sit in moduli space. So this is not very surprising. But really the new point here compared to just supergravity calculations is that you have this additional set of states and a full U-duality multiplet of states running around. So this is again this BPS enhancement of supergravity. Now, how do you do these kinds of integrals? I mean, you use the standard methods of usual Schwinger and Feynman parameters to reformulate this thing. So you turn it into some exponential. Now S and T are the Mandelstam variables. You have to sum over permutations as well. And now here, this is where this BPS mass comes in. So this is the only place where you have a dependence on this parameter or on this momentum gamma that you sum over. And written in this form, I'm not aware that this can be done in closed you get a closed expression for this sum and integrals. So of course, what you do is you go to a low energy expansion where you expand out in powers of S and T. And there's one term here which would be gamma equal to 0, and this is where you just have pure supergravity, so you have no enhancement with BPS states, and this is known to have a sort of lock behavior, and corresponds to the usual supergravity calculation, and you just remove it if you want to have only analytic terms. So I will now expand out in S and T and do the sum, but exclude the gamma, where gamma is exactly the 0 vector point.
I have a question.
Yes, please.
Before you tell the details. So this the theory that you're writing down is supposed to, supposed to somehow be the answer of string theory, right? You cleverly guessed what the only things that go in and so on, right?
Exactly.
So why are there no UV divergences? Is it because of supersymmetry?
I'm not sure that I said there are no UV divergences.
Are there UV divergences? Okay.
There are
the string theory will not, but if you truncate it, there's always supposed to be, unless something is special, right?
Yeah. So here there are, I think, let me try to remember. So I think there are, of course, supergravity has UV divergences in certain dimensions, right? For certain, like the R to the 4 term has a UV divergence in 8 dimensions and things like that. So this is something that you will see reflected in these answers that I'm going to show you.
Okay. And the other question was also about formalism. So in this exceptional field theory, one criticism often is that it's not a local field theory, right? Because how can you include both the momenta as well as wrapped objects for a given size of the compact manifold, right? And again, is it supersymmetry that allows you to somehow include both and have a sensible theory?
So I'm not sure that I share this. So one criticism is that of exception field theory that, locally you can make sense of it because you always have the section constraint, which means you have to choose like a U-duality frame. And that U-duality
No, that's not the one I'm talking about. I'm just saying that it's not an effective field theory, right? Because you're including both KK momenta and wrapped branes, but then what value of the size of the compact manifold is it effective in? Right. One of them is effective when the radius is large, the other one when the radius is small.
Yeah.
Right. So somehow does supersymmetry save you here, or?
Yes. I think the answer is yes, but I think I'm trying to give a better answer even, but.
I guess if you're saying that if you know already that nothing else contributes, then you don't need it to be an effective field theory. Then it's just some infinite sum which you can do, something like that.
Yeah, but certainly, here, I'm not claiming that the effective string theory. Sorry, I'm not claiming this is the effect. This exception field theory is the effective action of string theory in all possible contexts. I'm just using it as a tool to compute these particular amplitudes, right? Because I know, this is the theory that contains all the states that can possibly contribute to this particular order in alpha primed, and so I'm just using this as a tool to do
the only information you need here are the masses. You're not worried about couplings because somehow they'll be suppressed or something.
Well, yeah. So sorry. No, of course, here when I write this thing, you need to have something. I'm writing here avoid full Feynman rules in the paper, which is a few years ago. We have a discussion of the full Feynman rules. So you really need to know, of course, how the different states of exceptional field theory couple together so that you can write down these effective diagrams. So you need details about this, or you rely on details of this exception field theory and the coupling of the fields in the exception field theory. But at the end of the day, what it reduces to, and this is why I was sort of short-circuiting here, is that the only dependence really is on the mass.
Yeah. So in this diagram, there is no sort of I was referring to the self-coupling of the extra states. So the external diagrams, external legs here are gravitons or something, right?
That's right, yeah.
Yeah, so in this diagram, there is no self-coupling, but is that always true?
So there is, no, of course.
Is there a 3-point function of branes, for instance, whichever?
Yes.
There, I see that also.
So indeed, so this is a one loop thing. Later in a moment, I will do 2 loop things where you will also see vertices that couple the higher point.
Thanks very much. All right, thank you.
Okay. Good. so as I said, so I will take this amplitude and go to the low energy limit. And if you do this, you expand out. These are the first two terms that you find, written in a very compact form. And before I tell you what the notation here is, I want to say the lowest order term is just the r to the 4 correction. And the next order term that I've written out is the d4 r to the 4 correction. But of course, you could go on and generate more terms. Now, the notation here is such that this function xi is basically the Riemann zeta function, but in its nice number theoretic form where you complete it. So you put in some gamma factors and some factors of pi. This is just defined this way. And what is more interesting is this function that I call E alpha D with a certain label, S. And this is a sum. This comes from the sum over gamma, and just the sum over the BPS masses to some power. So this is, if you were in SL2, this would look like a non-holomorphic Eisenstein series very much. This is the generalization of the same concept to the symmetry group ED, to the exceptional symmetry group. And there's a certain normalization factor that I've taken out. So this is a function that is not written in this form, but in other forms, has been well studied in the theory of Langlands and other people having to do with Eisenstein series. And it comes out of this calculation because we do this sum over these BPS states. And here also this constraint is important in order to have a good automorphic function. So what this means is that this lattice sum here, restricted by the BPS constraint, is actually the same as a single U-duality orbit. So you could start, let's say, with a Kaluza-Klein momentum state and just consider all possible U-duality images of it and sum up their BPS masses with a certain weight. And then this is what you would find in this amplitude in exceptional field theory here. So you see here this, how you weight the different masses is different for the R to the 4 and the D4 R4. Now this is the result that you find, and so you can compare it to what was known in the literature by other methods. So for example, if you go to this R to the 4 coupling that I had on the previous slide, you compare it with what was known, and you will not immediately recognize it, but there are some identities called functional relations in the theory of automorphic forms that allow you to check that this is the exact correct result. And maybe this is not so surprising because we said this R to the 4 coupling is half BPS protected. This was the sum where we threw in only half BPS states, and somehow this captures exactly as an auxiliary system what we wanted it to capture. And by the same argument, maybe it's not so surprising that if you go to the next coefficient function, you don't get the right answer. So this D4R4 coupling is only a quarter BPS protected. And so first of all, you would expect that you should also talk about quarter BPS states, and we didn't put them into the calculation. And the reason why you see that this is bad is because this actually diverges in some cases in a way that you don't want to. And yeah, as I said, I mean, it's partly related to the fact that you didn't talk about quarter BPS states. And the other reason is that there's no reason for this coupling here to expect that a one-loop calculation is good enough. You should also look at two-loop calculations in exceptional field theory. So I will now address the two-loop calculation and also how to make sense of this for other problematic point. So, so for the two-loop calculation, there are two different topologies that you have to consider. I'm not going to go through them in detail because actually running a bit low on time. So you again get some kind of Schwinger parameter integral over something that depends on these BPS masses. And this is what you get from the alpha primed expansion at the lowest orders in Mandelstam variables. This is what contributes to the D4R4, and this is what contributes to the D6R4. And you see in particular, there's no contribution to the R4 itself, which is why the one loop calculation was good enough to give the right result. One point that I want to make here is that now, because it's a two-loop thing, we have two BPS states running around in the circle, and they have to satisfy, again, this kind of BPS constraint, both individually, but also when you cross them. So this is for all pairs I and j. So now this is something that we have to make sense of. And for example, the first term here has this dependence on gamma, again, only in this kind of weighting term. So in order to make sense of this, I also give you what is this Schwinger parameter matrix. This is usual from two-loop Feynman diagrams. We need to make sense of this sum, which is now a sum over all these pairs relating. Sorry, so I should say, let me go back. Coming back to your question, Samir. So here, I mean, you have these gamma 1, gamma 2 running around, and they can also interact at this point here. And the interaction here is such that it restricts this sum to these particular choices of charges. Okay, yeah, so we need to make sense of the sum over two charges, pairs of charges satisfying this. And I'm not going to give you the details, but you can again do this by filtering, choosing some decompositions of these charge vectors and filtering them into nice orbits of subgroups of ED. And if you do this, what you get is that the dominant contribution, so now there are different orbits of pairs of charges. The main contribution is called the non-degenerate orbit. And it again comes out as something involving these sort of Riemann zeta functions, and again an Eisenstein series, but now on a different node. So d-1 is different from what we had before, and also different parameter. And again, using these functional identities, you can check that the answer that you have here is basically the correct coefficient function compared to what was known from other indirect string theory arguments. In most cases, but there are also cases where you have to, I mean, there are some divergences here coming from the divergences of the zeta function. So you have to, this somehow has the right flavor, but it can't be the final answer. And why it's not the full answer is, of course, this was just the two-loop contribution. We also had a one-loop contribution that we need to take care of. And as I emphasized, we need to look at the quarter BPS states as well. This is only the contribution from half BPS states. Now, the quarter BPS states, they are somewhat problematic from this exceptional field theory point of view, because as I said, the section constraint is exactly the half BPS constraint, which means that the quarter BPS states will violate this section constraint. So it's not known how to describe these things that violate the section constraint consistently within some kind of enhanced supergravity theory. So there's no quarter BPS exceptional field theory. So this is a problem from this point of view. And we have two different answers for how to deal with this problem. So one problem is sort of ad hoc, where we just say there were divergences coming from the one loop amplitude. Let's just adopt the approach that the renormalization prescription is such that you remove these divergences altogether. So in some sense, you throw away everything that comes from one loop. This is something that you could just, looking from the renormalization behavior, let's say, of exceptional field theory that you could take. Something that is maybe a bit more satisfactory is that you could also look at string theory. So string theory, of course, has these quarter BPS states. And one way of realizing them is choosing some frame where these are strings where you have both winding and momentum, so it doesn't look very local. And these things are not level matched. So the quarter BPS states are, you have winding and momentum, but not in a level matched form. This is something you can easily characterize as string theory states, but it doesn't have U-duality invariance, because this is only in a specific frame. So you write down the corresponding contribution in this frame, and then you enforce U-duality by hand. And this is something that requires an elliptic continuation, and we looked at this somewhat carefully in this paper, and used this also to make sense of the contribution of quarter BPS states. The good news is both approaches, whichever one you take, actually leads to the same answer, namely that this you can use this method to get the fully correct quarter BPS coupling from these methods. So this is just finishing the point that you can use exceptional field theory methods to reproduce completely these half and quarter BPS couplings that were known indirectly from string theory before. Now, the title of the talk is 8 BPS states, 8 BPS couplings. So clearly, I now want to take the same approach and push it to the next order. The corresponding function coupling is, let's see, so it's 14 orders and derivatives, D6 R4. And there have been studies of this thing in different dimensions with conjectures and partial answers that I've listed here. But our approach was now to use this, this exception field theory machinery to understand in more detail how this is uniform throughout the dimensions and to clean up some open questions. Now, I showed you a moment ago this two-loop calculation of exception field theory had this sum over pairs of charges, and for the next order in the low energy expansion, you actually get a coefficient function that here depends also on these Schwinger parameters that sit in this matrix omega. And that this particular thing here comes up is not so surprising, because the people who studied this from the point of view of two-loop string theory looked at what is known as the Kawazumi-Zhang invariant, which is a particular invariant on the moduli space of genus 2 Riemann surfaces, and which of course depends on the complex 2x2 period matrix. And this is the tropical limit of this, where you only look at, let's say, the imaginary part of the period matrix. And this is known, this invariant is known to come up in this two-loop string calculation, and it's not surprising that we find sort of this field theory limit in the exception field theory calculation. Now, this is the answer from this BPS enhanced or exceptional field theory two-loop calculation. And the first thing that you want to check is that I mentioned in the beginning that the couplings satisfy very strong differential equations. So now you want to check that this thing here does satisfy the right differential equation, and you can do that. So you just take derivatives here on the moduli space and check that this differential equation is satisfied. And what is particular, this is why this 1/8 BPS coupling has been so hard to get a handle on, is that this differential equation has this inhomogeneous term. So it has a quadratic term in an automorphic function on the right-hand side, which is a very unusual kind of automorphic differential equation. So this equation had been known for some time, and there are also, this is only second order scalar equation. There are also, for the other Casimirs, tensorial generalizations. And what we checked is that this function here satisfies all the equations. So this is already good and encouraging that it satisfies the right equations, but this is only one specific two-loop calculation. You also have to consider the one-loop and the three-loop calculations in exceptional field theory. I'm not going to show you the details of that. They contribute to homogeneous solutions of the same equation that you have to fix using boundary conditions normally, but here it just comes out of the amplitude calculation. And again, I mean, all the calculations that you do in exceptional field theory, as I keep emphasizing, they only involve this half BPS state. So somehow now, of course, you want to include the quarter BPS states and so on, which means that you have to renormalize the exceptional field theory answer in the right way. If you do this concretely, you get from these methods a candidate for this coefficient function as an automorphic function on ED for all possible values for external space-time dimension D at least 4. So, well, we have a candidate, as I say. So what do we do? And this was a large part of the work of this very long paper in January. What do you do in order to check this candidate is you have to check that it matches the right boundary conditions, which means that it has to have the right limiting behavior when you go to boundaries in moduli space, like the weak coupling cusp or the weak coupling limit. So this is one of the parameters in phi, and now you have to take this ED group and branch it out under the corresponding weak coupling limit, which means that you look at things that are not invariant under U duality, but only invariant under T duality. So you take the 56 components of the charge gamma, this is the 756, and you decompose it in this way under this T-duality group. And you write out this sum in this decomposition. So the first thing here is just the, now you're on a 6 torus from the string theory point of view. So you have momentum and winding quantum numbers. Then you have things coupling to the Ramond fields. And then you also have these dual coordinates for this one. You take the sum here, you write out what is the section constraint. So it turns out the lowest order section constraint is just that momentum and winding are a null vector in this usual even self-due lattice. And then there are additional components of this condition here that mix the different parts of this U-duality charge. And again, this is the half BPS constraint, which means that here this is a null vector. If you want to have quarter BPS states, you would have to relax this. So this is the usual violation of level matching. Okay, so now what we did in the paper is that we look at this expression here. We take these charges and we just populate each of these terms consecutively. So clearly this is something that becomes more and more complicated the more and more charges you consider, but we did this over many, many pages. And then using some analytic continuation, we were able to carry out these partial sums and also these integrals. So once you do this, you find that the candidate that we had from this exceptional field theory, it's exactly correct. So it's really reproducing all the expected perturbative terms, which means that it includes all the right string theory perturbative answers. And here I've written out, so what is known, this is a BPS protected coupling. So this only has a finite number of loop contributions, namely 3 level, 1 loop, 2 loop, and 3 loop, and lots of non-perturbative terms. And we were able to extract from this slightly complicated formula that I had on the previous slide, we were able to extract all of these things with exactly the right coefficient and functions. So these are perturbative string things that you get from doing something on the genus H Riemann surface using some kind of theta lift with a Narayan partition function. So for example, the one loop contribution that you want to get is a combination of automorphic forms on the T-duality group. And we were able to extract out exactly these terms from the candidate that I showed you. And again, it's important that you do all the things, so you renormalize all the functions correctly, and you also have to throw in these extra quarter BPS states. And let me just say, so other things that we showed in this paper is that we also get the right threshold or divergence structure. So this is coming back to the question that also Samir asked a moment ago. So these things are not meant to be completely finite. So you can detect the supergravity divergences, and we were able to extract those. We also checked that there's a nice pattern when you decompactify. So when you go from dimension D to external dimension D plus 1. This is a similar calculation where you have to do these lattice sums, so it's also quite involved, but we were able to check that correctly. We were also connecting to previous results or conjectures by Boris related to specific dimensions, which were done in a different string theory motivated framework. So we could check that all the answers we gave in this formalism using exceptional field theory agrees with these. And maybe also something that is interesting in the context here is, I told you that there are these additional non-perturbative things coming from instanton backgrounds, which we could compute only in some cases, not in all cases. And for example, what we could do is we could look at the 1/8 BPS stack of, let's say, this combination of D1, D5 branes on the 6 torus. So we could compute where these are nicely co-primed. So this is the primitive configuration of this D1, D5 system. We could use this very complicated formula with this double sum that I showed you on the previous slide. And after massaging it for some time, you could extract out of it the indexed degeneracy of these 1/8 BPS configurations, and it comes out exactly in the right way that people had been deducing many years ago using counting problems for black hole BPS black holes. So this is this is just a summary of some of the results. Here, what I tried to show to you in this talk is that we really have a very direct way of computing these couplings. So this extends, because for this d to the 6 r to the 4 coupling, not all instances were known. This extends this to all possible cases in d greater or equal to 4, and it unifies them in this BPS enhanced field theory manner. We could also check in some cases, the counting or indexed counting problem of BPS states, of 1/8 BPS states. It's a very nice and powerful tool. This, of course, is something that I said. And also what we found is that we had some way of dealing with these quarter BPS contributions. So maybe for people who are interested in these exceptional field theories, this might be an interesting point to connect to, because it's not known how to write down an exceptional field theory with 1/4 BPS states. And here, what we had to do in this context is to really find sort of an effective way of dealing with it. So maybe there's a way of using what we have been doing in a more systematic way to generalize this exceptional field theory in some way. Something that, of course, would be very interesting to do, that I don't have much to say on, unfortunately, is everything that I talked about was in the toroidal compactification context, so only maximal supersymmetry. How much of this can you generalize to other compactification manifolds, other theories? And also you might ask, as was already done, how can you use this in any way to go beyond the D6R4 to learn about the non-BPS states? And I have to say that I'm a bit skeptical there, but it's probably worth exploring this to some detail. Thank you.
All right, Axel, thank you very much. Thanks very much for this very nice talk. Are there any questions?
Can I ask a question?
Please.
What goes wrong if you try to relax the section constraint trying to include more BPS states?
So what goes wrong in exceptional field theory is that the way that this is formulated is really as a theory. Let me go back to, oops. Let me go back to the slide, as a theory on this extended space. And there is some kind of Lie derivative acting on these internal and external coordinates, which is like the algebra of diffeomorphisms. And what goes wrong if you relax this section constraint is that the algebra doesn't close anymore. So you don't have really a consistent set of gauge transformations geometrically on that space.
Maybe you have to extend the space so that it closes in a larger space.
Yeah, maybe you have to do something like that. But somehow, I mean, yeah. So this is what goes wrong really in when you want to write down the exceptional field theory as a field theory. Here, of course, you could ask the question: what happens if I just take sort of this, let's say, effective point of view where I have these sums? What happens if I remove this condition here? Or I replace it by the quarter BPS condition? I allow for more states to run around in the circle. And in that case, I think it's not possible anymore that, for example, here I said you get these nice Eisenstein series. So once you relax this this half BPS condition on the gamma sum, you will not get Eisenstein series, which are eigenfunctions of the Laplace operator anymore. So somehow there's a nice connection between these different concepts and the automorphic differential equations that also seems to be violated as soon as you throw in additional states into this naive or effective loop amplitude.
So it means that if a generalization exists, it must be not so naive. Yeah.
Yes, exactly. So I should say that, well, I mean, this is not something that really directly connects to this problem here, but people have been talking about violations of the section constraint also in the context of exceptional field theory. And typically this is in the context when you do some kind of generalized Church-Schwarz reductions or things like that. So because you can also use this formalism to construct gauge supergravities of different types, and there sometimes you have to violate the section constraint, but this is not directly related to the things that would be needed here. So yeah, I think it's an interesting question. I mean, how can you go beyond this? Do you have to enlarge the space? Do you have to modify the gauge transformations on the same space? What is the right way of dealing with these quarter BPS things? And I think if one wanted to tackle this problem, maybe a good place to start would be double field theory, where one only has this kind of null vector condition on the momentum and winding thing, so one doesn't have to care too much about the d-brane, so it's only the string, momentum, and winding. And also there, normally one enforces that winding and momentum have to be level matched, and what goes wrong if you relax this? How do you go there? And people who work on string field theory have been thinking about this to some extent, but I don't think there's an answer that has been achieved.
I have a question, but I've been asking a lot, so I'll wait if somebody else has.
Well, go ahead, Samir.
Okay, towards the end, you mentioned something about 1/8 BPS state counting.
Yeah.
Can you just expand on that? The point sort of went past me. Is this a check, or is there a new way to calculate those numbers?
No, so in that case, it was for us almost there here. So for us, it was more a consistency check. So these numbers, they had been calculated many years ago. And of course, it's expected that this 1/8 BPS coupling knows something about these degeneracies. And so for us, it was a check to get this thing out again. What is our formalism? I mean, when you look at the paper, also gives you, in principle, something for the degeneracy for other configurations of branes. So let's say not this projective or primitive kind of vector, but you can also have more complicated arrangements, and we have some arithmetic or combinatorial formula what should be the corresponding counting function, but it's written in a very involved or convoluted way, so that it's not something that I'm not sure that this is the best way of writing it and how to use it. Yeah. So, but for us, really, it was more like a consistency check of our ansatz.
But the way these numbers are derived is there a new method to do it, or I mean, does it come out of your functions in some limit or something like that, or? So really what we do is we look at this thing, which looks very different from what you would normally look at for these counting functions. And we do this thing that I was describing here. We look at this sum over these two BPS, half BPS things, and we fill it up step by step. And we keep track of all the possible terms involving the non-zero Fourier coefficient. So this is like, what we want to achieve is the Fourier decomposition of this automorphic function, and the terms in this Fourier decomposition that don't depend on that depend on the string coupling constant in a polynomial way. So this is like the zero Fourier coefficient, and then there are these exponentially suppressed terms. So where these counting functions appear are in these exponentially suppressed contributions because they are non-perturbative. And so you have to look at this, and in this way, I mean, you could say it's a new way of computing these functions, because you really have to do a very complicated analysis of this this object here to arrive at this counting function. And yeah, okay.
I don't know whether Boris wants to chime in on that, but it's from that point of view, you could say it's a new method, but I'm not really sure that I would say it's a recommended method for doing that calculation.
Okay, any other questions? So if not, let's thank Axel again. And well, what? Right, so Right, so we'll resume again in the afternoon at 2 o'clock Lisbon time. So thanks very much and bye-bye.
Bye-bye.
Bye-bye.